what you saw was a few interesting characteristics. You saw that the communication pattern was preordained. You always had a source and a desk, and they were picked ahead of time. Most of the communication was in the form of load store operations. This is a direct access from the CPU towards a memory in some region. However, if you look at the more successful architectures for this space, they often had embedded DMA engines because load store in itself is actually quite inefficient when done at large scale and repeatedly over a very large memory block. They had fairly coarse access control because you didn't want to spend a lot of time when a CPU is talking and communicating in trying to check that its access is valid. So access control was implemented in either regions or pages or some very large space. The problem with a design like this, however, was latency. As you started scaling these things up, the latency started scaling in the wrong direction. So they came up with all kinds of fancy topologies. There were star networks, dragonfly networks, 2D, 3D toruses. If you're interested in computer network topology research, this is an area I encourage you to understand better because a lot of very interesting results came out of it. However, the problem was physics. At some point, the incremental scale got really, really hard. You couldn't keep building bigger systems and then saying that I will paper over it with the new topology. So then came the rise of Borg. What is traditionally, for people who don't know, Borg is the internal code name, nickname for Google's overall large-scale enterprise management system. And these kind of systems had a different characteristic. The characteristic was the workload was divided as or defined as something that was a worker to a load generator relationship. The load generator was typically internet type applications, and the workers were sharded and replicated. Why this was better than the previous design was that this allowed resiliency. And because of this software managed resiliency, the system could now scale from a few thousand nodes, or not even a few thousand, up to 1,000 nodes, to millions of nodes. And this is really what all of us now know as cloud computing or hyperscaler infrastructure. All the communication in this model is wrapped inside an RPC. It's a software managed communication. CPUs don't just talk directly to each other. RPCs are built in. And the data pipelines can be imminently reconfigured. You can just decide that for the next step, I'm going to send this data to a different node, I'm going to do different kind of processing and send it back. It's not hard-coded, it's not hardwired. And because the elements are heterogeneous, while you got very, very high aggregate throughput, the tolerance to latency had to be very high because you didn't know who you were talking to. At any given time, you could be talking to 3 or 4 different nodes, and they could all have different characteristics along the lines of what Ritu was saying earlier. If you look at a system like this, they were typically built around TCP and ECMP as the base criteria. It works really, really well for over-provisioned links. Doesn't work so well if you were trying to work in an environment of bounded tail latency, something that I know a bunch of people in this organization are looking at. It was also designed for median performance, not max performance. For example, fairness requires you to never run your network at max throughput. I'll pause there for a second. I don't know if this is a point that everybody understands very deeply. If you were to build a network that is 100% fair, it can never reach peak throughput. If that point is not clear, we can talk about it at the end. Hopefully have some time for Q&A, but I would like people to think about it a bit. The other thing that emerged out of this was that cross or factory topologies ended up providing the best, most resilient bisectional bandwidth. This was not built for no failures. It was built such that failures could be handled effectively. And the net loss of throughput in the case or in the face of failure was better than all of the alternatives. Redundancy, failure handling, telemetry, etc. were all sort of abdicated. They were left for TCP to handle. And the core of the network didn't really do much. In fact, most of the core of the network was really a simple packet forwarding environment. This changed a little bit with the advent of something called RDMA Rocky, which we talked about in previous two sessions. And RDMA and Rocky were brought in to fundamentally allow the application to bypass the operating system. The simple way to think about what Rocky changed relative to everybody else is that instead of doing a system call to move a buffer from an application into a different thread running on the same CPU, they moved that processing out to a processor inside the NIC, and the buffer was sucked in directly from the application itself. This step allowed the avoidance of a system call, allowed the avoidance of a whole bunch of locks, which created variability and created latency in a standard operating system. And as the network speeds got faster, it became more and more relevant that you had to avoid the CPU and variability in the CPU from becoming a bottleneck in your communication. While we understand how those things work, I wanted to talk about a few other important things as well. At the end of the day, all high performance distributed computing, actually all distributed computing, is about memory, right? If it's not about memory access, then you're doing something wrong. So there are a few ways you should think about what memory access means, and some of them are becoming incredibly important in the context of machine learning. The first is synchronous access versus asynchronous access. And it's kind of, the terms are, in my mind, a bit reverse labeled. But in machine learning, what is meant by synchronous access is when everything effectively operates as a single synchronous batch. You start a batch at the beginning, and when the batch is completed, then you call it done and you move on to the next batch. This allows for maximum pipeline efficiency, but it also means that your pipeline cannot move in parallel. Everything only moves when the previous step is completely completed. Asynchronous, on the other hand, is a great way for people who are looking at distributed computing. You know, asynchronous systems tend to scale better when you're having millions and millions of operations in flight. The ability to be able to launch all of them and not have dependency and not have to serialize generally gives you higher efficiency. However, in the case of things like machine learning, where you eventually have to reconcile all your state, it creates new challenges or different challenges. The other thing that you have to think about is some of the communication is often load store, like Sadanand was talking about. If you're doing something like tensor parallel, if you want to be able to scale that up in an interesting way, you want to be able to keep all your memory coherent and be able to read and write the particular elements that you're looking at and be able to reconcile them using the all gather plus reduce step as fast as you can possibly do it. And as fast as you can possibly do it means you're not going to buffer. You're going to do it directly as the completion event of that CPU. The other alternative is DMA or RDMA, where you create large bulk blocks of data and you move it across and you say, okay, now that I have this multiple kilobytes, megabytes of data, I can reconcile it in one batch and move on to the next step. These four types of operations fundamentally are, you can take what Sadanand was describing as the different collective ops, for example, and all of the collective ops that he broke down into whether they were reducers and gathers and FSDPs and so on and so forth. You can divide all of them and say that they all map to one of these four types of access patterns that the underlying hardware has to be able to implement. And why are we talking about this? We'll talk about that in a second. Oh, that's why are we talking about it? We're talking about it because if you look at what a large-scale ML system looks like today, it looks fundamentally like this. And I'll give you a second to look at the picture and absorb it a little better. The green links are what were described earlier as scale-out links. I call them RPC links. The blue links are scale-up links or IPC links. And if you look at the general structure of modern ML systems, they look roughly like this, right? And what does that give you? What that gives you is a scale-up domain a scale-up domain that communicates between the accelerators on this path and potentially the CPU if it needs that, and a scale-out domain where the accelerator communicates to a PCI switch that Rintu was talking about, to a NIC out to the network. The implication of this is, if you have been following along, is that it has to solve both the problems of the scale-up systems and the scale-out systems at the same time. Because the solution that it is aiming for is neither one of the first two solutions that we looked at. Now, there are a few things that are operating in its favor. The first thing is that the applications are now fairly standardized. Like if you look at the history of HPC computing systems, for example, HPC computers were built to solve anything. People were allowed to write code that were doing random things. You could dereference a pointer in the middle of a loop and it had to do the right thing for it. Whereas for most ML systems, much of this has been normalized into something that looks like CUDA, which is an assembly language-like construct, and upper-level constructs that run through frameworks, where the structures are fairly normalized. You cannot just do random things. And the scale-out communication is all normalized through this thing called a CCL, which again restricts the type of operations that you can do and normalizes it such that you can accelerate only that small set. However, a modern system which has tens of thousands, maybe hundreds of thousands of these nodes, still create a new set of problems. And the new set of problems is that they are trying to attempt, or they have to try to attempt, to solve a problem that neither of the fundamental structures were built to try to actually solve. Right? So the scale-out network now needs to be almost 100% free of faults. And the scale-up network now needs to be able to handle a node count and a node size that is much larger than most of the protocols that were built to be able to solve such a problem. In addition, you have the problem that if you were to go and try to remap all of the CCL patterns that we were talking about earlier to these kinds of systems, you will find that the mapping is not always straightforward. There's a lot of imbalance between how much bandwidth is available on the blue links versus the bandwidth that's available on the green links. And depending on the algorithm that you're looking at, it may lead to a thing that you do not want and do not need, and you have to re-architect your entire pipeline. The system layout is, well, I guess it's the same thing. The system layout is today also a function of that. So whether you're putting more network links or you're putting more scale-up ports is a choice that every designer is having to make for every component that they design for every generation. And this gets much worse when the most popular ML architecture or the ML pattern changes over time. Like was mentioned earlier, 4 or 5 years ago, DLRM was the most important thing to do in ML. Today, LLMs are the most important things to do in ML, and who knows, next year it will be something else. And the system designs that were built to be able to address those specific characteristics have changed over the years. And today, the changes are actually quite limited because there is not much you can do. Oh, and the last thing is the implication of efficiency is actually measured in something called MFE, which is, I think, model flop utilization is, I think, the full expansion of that. And what that really means and what that implies is that if you have failures in such a large distributed but synchronously computing system, the problem is your system has to stop. And the way most of these guys are building it today is that every time you see a failure, you're going to take a stop, you're going to roll back to the last checkpoint, and you're going to restart your computation. Now, think of that as what you're trying to achieve, right? Like, so if you are trying to run, let's say, a 16,000 node system, and you are connected, in this scenario, most of the time, the connections for these green links will be optical. Optical links for a 16,000 node system means that you will probably see one optical failure every 7 to 10 hours. That means every 7 to 10 hours you will lose connectivity to one of your accelerators. And losing connectivity to one of your accelerators means your job is now done, right? Because no one is saying, oh, it turns out that column of that matrix I didn't actually need. I can just throw away the results and keep moving. So you have to go back and reconcile. So the way people have addressed that problem today is that they take checkpoints. So if you have a 7-hour failure domain, maybe you take a checkpoint every 30 minutes. And in the case of a failure, you will roll back 30 minutes, effectively losing 45 minutes on average every time you see a failure. And those 45 minutes of computation is now completely lost. So if you take that over the full runtime, you're going to see a pretty significant loss in total computational efficiency of your system. And this example I covered only covers optical failures. There are many other kinds of failures that you can end up with, and therefore redundancy and management of failures is actually a significantly important thing in these modern machine learning clusters. Okay, so let's switch gears a little bit to talking about how components have been designed on the networking side of this. So today, if you look at how people are thinking about it, there are three broad categories that you can think about. We call these are our terms, we call it the micro-NIC, the traditional NIC, and the mega-NIC. And you'll see the Enfabrica logo showing up on the mega-NIC, but you don't know what it is, so bear with me, you'll find out soon enough. But for now, think of what the topological or the architectural constructs look like. The micro-NIC is, like I think Sadanand was implying, a very, very simple NIC. It's embedded into your accelerator. It doesn't have any sort of external accoutrements, but it has to be a complete embodiment of a transport. It takes bytes from an accelerator and shoves it out to a network wire. Needless to say, in a design like this, the switch that you connect into, or the networking layer you connect into, has to be able to absorb all the complexities of managing a multi-node network and variable latency and variable distances. A traditional NIC is a traditional NIC. I'm assuming most people here are familiar with at least what it means in concept, and it just connects to a switch. In modern ML systems, the way they have addressed the networking complexity of this is by making the network that you connect into be defined as something called a rail network. That means every GPU talks to one NIC, talks to another GPU through its one NIC, and the communication between these pair of GPUs is through an isolated network, which is the rail that these GPUs live on. It's an extremely over-provisioned system, but it's done this way to prevent surprise congestion events happening in the network. And this way, the overall communication orchestrator can be in total control of what kind of congestion it will experience when communicating. And the last one, as we said, is a mega-NIC. And if you look at what the mega-NIC does, what's different is it's got oodles of bandwidth coming from the accelerators into this device, and this device effectively acts like the first hop, NIC and TOR combined in one package. I think we've covered most of the meta points here. So I think I'll highlight a few, right? So if you go with the micro-NIC design, the transport has to be embedded, it has to be in gates. It's very, very unlikely that you're going to have any kind of flexibility in there. What you put in there is going to live with you for the lifetime of that accelerator. There is no adaptability in that system. And it is a completely end-to-end unique system. You have to have both endpoints running the same micro-NIC. You have to have everything from the accelerator to the switch understand all of the traffic flows, because you are now integrating into the thread's communication pattern. A traditional NIC, I think, is a little better understood. The problem that a traditional NIC has had, like if you look at the last 20 years of what NICs have evolved towards, and I will assert that it was my product that started the trend, the goal has been to put more and more packet processing into such NICs. And when you put more and more packet processing, you put more and more latency and computational complexity. Right? These devices traditionally are built for being able to handle tens of thousands of flows at gigabit speeds with deep packet inspection, and are actually not that efficient if what you're trying to do is 10 flows at terabits each. And can you make it go faster? Yes, you can, but the fundamental architecture is actually optimized for deep packet processing, which is not required for these large ML systems. And Yeah, and so in comparison, a MegaNIC would allow you to have much more precise understanding of queuing, of traffic patterns, be able to offload and provide adaptable compute elements, and adaptable to transport, and congestion control elements, such that you can realize a better system architecture on demand and be able to deal with system architectures that you are exposed to for the current form of acceleration. Okay, so what are we building? So what Enfabrica is building is a chip that fundamentally occupies a spot that looks like this. So if you remember the picture before, this is what the picture in the future looks like with us. So you notice that each of the chips, each of these instances of, each of these things called the ACFS are instances of our chip. ACF stands for Accelerated Compute Fabric Super NIC. And if you look at what it's doing is it's sitting at the nexus of the scale-up and the scale-out networks. And it has a very wide radix scale-out network, and it has a very wide radix scale-up interface as well. Now, what is interesting about it is, on this side, you can connect CPUs, GPUs, and what is not shown here is actually memory as well, because that device can speak PCI or CXL in a coherent way. And the other thing to notice is, while each of these instances are creating a factory resilient, reliable network on the Ethernet side, it is actually doing the exact same thing on the scale-up side as well. So now even your compute elements have a cross network attached to it. So if you were to remember, or if you do remember, the complex scaled out design that I was showing you earlier of what modern ML systems look like, with an ACF in play, the picture would look significantly simpler and look like this. In fact, if you really want to, and that requires a bunch of industry collaboration, you could actually even remove these links and just fold them back into the ACF and allow the ACF to be the complete scale-up fabric. Okay. Oh, sorry, that was the animation. I spoke too soon. So yeah, you could just take those out. So internally, this is what the device looks like. It's got 3.2 terabits of network bandwidth. On this side, shown by the green arrows, it's got about 5 terabits of PCI fabric bandwidth, which can be provided as 160 lanes of PCI 25. And this thing is a special thing. We'll talk about that in a little bit more detail. But the important thing in this picture is, if you have been following along so far, you would have said, or you would think, that this device is an Ethernet switch, a PCI switch, with a NIC sandwiched in between. That would be the wrong conclusion. It's actually nothing like that device. The device is nothing like that. What it is instead is effectively a memory controller and a data mover, or what we call a copy engine. And what this copy engine can do is it can effectively collect data from any collection of interfaces on either side and convert it into any collection of interfaces on either side. So when you want to build a network packet, it collects headers from some port, payloads from some other ports, and serializes them out on an Ethernet port, and vice versa. When you get a serial stream coming in from a variety or a collection of network ports, it can convert that into memory addresses and write them out as headers into one port and payload into another port. There's a diagram coming that will help explain that a little bit better. The other thing I wanted to say here was, no, that's pretty much it. So at a high level, at a very simple level maybe, the PCI switch is a full-featured PCI switch, the Ethernet switch is a full-featured L3 router. Maybe we can come into the details a little bit better later. Okay, so this is the sort of the data path flow diagram. So if you look at this, what this is saying is, if you remember the color coding, greens are the network ports, blues are the PCI ports, and if you follow this direction, What the device allows you to do is collect packets that came from, let's say, multiple ports, put it into a thing called a virtual output queue. For people who have been building switches and large systems for a while, you know what a virtual output queue is. Actually, maybe I'll ask the question, how many people here know what a virtual output queue is? Two is a small number. Okay. The idea, a queue, I'm assuming everybody knows, you know, if you have packets, you queue them and you forward them. A virtual output queue doesn't actually queue anything. It just says, in memory, I create a linked list of packets that are supposedly queued. By doing it that way, you don't have to queue the actual device. When you want to process a virtual queue, you just process the linked list, and by following the next pointer, you actually drain the queue in the order in which you expected. Hopefully that made sense. So what we are doing here is, we are saying that when the packet comes in on one of these network ports, the header, and actually just the metadata representing the header, goes into a virtual output queue, shown by these three red arrows. The virtual output queue then gets drained into the PCI domain based on buffers that have been posted on the PCI domain. So what you've done here is you've then said, packets can come in on a collection of ports, effectively get serialized, and then get deserialized onto a collection of network ports, PCI ports. That's the control path. The data path, shown here by these blue arrows, if you notice, is direct. So if each of these ports, let's say were 100 gig ports, let's say this was 100 gig, that was 100 gig. What we just did is we created a 300 gig NIC. Because each of the data path can support a full 100 gig of data transfer. Right? So the data path is completely in parallel. The control path is relatively small because headers and compressed headers are significantly smaller than the net payload, so you can do that separation and get away with it. And this is a very simple way to make it such that the end-to-end flow control and the end-to-end condition control and the end-to-end data path efficiency can be achieved. And I just realized I didn't talk about the flow control part of it. Notice this virtual queue. This virtual queue is accurately representing the state of the other side. Now, there are virtual queues in both directions, so if you were sending, you would have a virtual queue representing the network port. If you're receiving, you have a virtual queue representing the PCI ports. And these virtual queues, if they're not draining, it means there's congestion downstream. You don't need to guess, right? This queue is, the way this queue drains is when the host consumes the data and says, I've updated some doorbell. So that is a precise signal that the host has consumed the data. If this network queue is not draining, it means we have PFC up here and the upstream switch is blocking any kind of data transfer upstream. So the signals are 100% accurate. If you were blocked on the way out, we would just not fetch data from the actual data store, from the original memory. If you're on the way in, if this queue is building up, we will send a signal telling the transmitter on the other side to stop transmitting, because we will soon run out of buffers to be able to absorb the data. This is a pretty big leap in terms of systems that are being built today. And I said it actually solves a lot of problems that are being attempted to be solved by using more fancy condition control schemes with a much simpler architectural construct. The other thing that's unique in this system, and I want to go back to that point for a few seconds. So if you remember what I said, this fundamental difference between an RDMA NIC and a normal NIC is that the transport is built into the NIC itself. It's not so much about Rocky, it's about whatever transport you're trying to do, that transport has to be in the system. Because if that transport is not working correctly, then you're going to have a problem. So what we have done is we've said, instead of trying to embed a transport in every NIC, which makes it hard to be flexible about it, we've extracted it all out and sort of landed it in an attached processor. This processor can run any user-defined transport that you can imagine, but it has the ability to execute control by way of being able to steer packets, steer buffers, and steer control on a per packet or a per flow basis. This enables a much simpler model. So like the question that was asked earlier, we can run RDMA over TCP. Actually, we do. That's one of our baseline implementations. Because the transport itself and the system implication, because TCP by itself has no real problem with performance. The problem it has is the system call in the standard TCP implementation and all the locking structures that it has to experience. By doing it this way, we run standard kernel TCP on this CPU, but this CPU doesn't have any memory effects, no payload data ever touches it, no other cache effects hit it. There is no syscall because we communicate through a direct queue between the GPU and the processor. So you eliminate the problems that make TCP not run fast, but don't change the protocol itself. So from the wire, you don't see much of a difference. Okay, I know we are running a little low on time, so I'm going to breeze through some stuff. I don't know if much of it will land, but we can hopefully keep some time for questions. So, like I said in the beginning, if you think about the problem is always memory. And since I'm talking to a bunch of academics, I offer a taxonomy that I've been trying to push onto people. If you like it, please take it. And this is like you have the 7 layers of networking. I'm trying to redefine what memory access hierarchy looks like, right? So if you think of L1 as dereferencing a pointer in your cache or in your main memory, L2 is sort of NUMA access, L3 is often a mem copy or something like that going out to near far or far memory through CXL, and L4 and L5 are SSD or some kind of network attached memory. A thing to notice in 2025 is that notice this bandwidth is actually higher than that bandwidth. I can get you memory from the network faster than you can get it from locally attached DDR, which is actually a pretty big inversion. Of course, the latency is also inverted. You go to 2 to 4 microseconds as opposed to 150, 160 nanoseconds. But this inversion is pretty big. So why does that matter? That matters because using a device like ours, you can actually do a lot of things in this L3, L4, L5 domain, and you'll see what those are in a second. So the first way to think about it is if you have a data center, which typically will look like this, right? So you have some collections of CPUs, GPUs with their attached memories, and let's say you have an ACF with memory locally attached to it, shown here. And let's say your taxonomy looked like this. What you can do now is you can basically say, in my data center, I have local memory on this GPU. I have memory that's not that far away, available through the ACF and its data copy engines. And I have terabytes of memory available to me in the network. What we've basically done is, in a design like this, is your entire data center is one large memory store. And it looks more similar to the first picture I showed you of what traditional scale-up systems used to look like, without many of the problems of a scale-up system, because there are all these memory transfers and memory copies are asynchronous and not coherent. Another way in which such an application, such a system could help you is, let's say you were building inference systems, a problem that many people have today. And if you look at the large-scale inference systems, one of the problems that you have to deal with is getting your context cache and your KV cache reinstated every time you have a user. And maybe I should take a step back and expand on that. Let's say you had 2 GPUs and 10,000 users. You have to recycle the users through the GPU at any given time. And you have to give each of the users enough runtime. So if you were to do, in the example that I just said, if you did the naive thing, and you just started adding more and more users to the fixed size of GPUs, your job completion time or your response time is going to start climbing. This is a fairly simple, predictable queuing theory curve. Using a scheme shown here, what you could do is you could store in a cache hierarchy the context cache and the KV caches and restore them into a much larger set of GPUs. By distributing which GPU you move the data into and selecting from a larger pool, or maybe the same pool, but now freely selecting from that pool, you can change your behavior curve to a much more acceptable one, where this red line is showing where you were about to violate your user SLA. And you can see this guy violates it around 45%, this guy violates it around 90%, which is a pretty significant change. Another way to think about it is, you can get the same performance with one GPU instead of two. Another thing we talked about, right, is resiliency and scale. So if you think about training systems, which now are beginning to get really, really large, I'm sure in India we haven't really seen that effect yet, but in large parts of the world, people are talking about 50,000, 100,000 GPU systems as not that large anymore. And if you're talking about a universe like that, the way those systems are being built, okay, so no one actually builds it this way, but this is more for illustration. So if you had a design where you had a 51 terabit switch, you would be able to do 31 ports of 800 gig down and 32 ports, of 800 gig down and 32 ports of 800 gig up. So what that means is you would have 32 GPUs connecting at 800 gig to this particular switch. And that would be your lowest latency single hop that you could build, single hop network that you could build. With a device like ours, you can make that number. And the reason why you're doing that is because why you can do that is because we've integrated that NIC and TOR first layer. So without paying any additional latency, you're getting the wide radix. And our device can do the packet spray and the message spray that is needed, such that you can now effectively create a 1,000-node network that is just one hop away, which is a pretty dramatic upgrade from that number. If you further this, what it allows you to do is you can build a 500K GPU network in two tiers. If you think about latency as being the single largest problem to solve, this is a very significant step forward. In addition, we talked about resiliency, right? So one of the problems, like I was saying, when you start building these 100,000 node systems, is that path diversity is a very big deal. And just having multipathing is not good enough, by the way, right? Because, so let's say you had 4 paths and you lost one. A traditional multipathing design, you'll say, okay, great, so I will pick one of the other 3 paths and take the 4th traffic onto it. Which means, now 2 of your paths are running, or 2 of your flows are running at half speed. Which means your straggler, your tail latency just went up, because you have 2 stragglers now. It's much better if you could say that I took the traffic from the 4th one and distributed it evenly on the other 3. Now you no longer have a straggler, you may incur a slightly higher latency, but your tail latency delta is much, much lower. And at the end of the day, your tail latency is your biggest problem with machine learning systems, because they are all pipelined. If they take higher latency, they take higher latency, but the pipelining should hold. What is much worse is if one takes a little bit longer, which means n-1 nodes are sitting and waiting while the last one arrives, right? So what our system allows you to do is to express resiliency and multipathing both on the PCI side and on the network side. And since the device is message and flow aware, it can make much smarter decisions about how the redistribution works in the face of failure both on the PCI and the network side. I could have gone on and on and on. So this architecture helps with things like Hadoop, things like Redis acceleration, memory offload, and so on and so forth. For people who are looking at what ML systems are doing today and how they will get used in real-world applications, the word RAG should be familiar. And that's what is today driving most of the real-world revenue-generating applications for ML. And a system like this can have pretty significant advantages to the entire RAG pipeline, not just the machine learning and computation bits, but also how data is ingested, how data from training is then replayed into inference, and so on and so forth. In terms of industry collaboration and sort of interconnects, this is the area where I think we are most looking forward to how people can use a system like this a system that allows you to move data more efficiently than a traditional overall system stack would allow you to do, and come up with new, better applications and improvements that makes the world of ML a better place. There is a lot of room in that area. I'm going to skip over most of this. There's a whole bunch of system implications of building a device like this, right? You get better SerDes locality, you are not consuming gates inside computational elements to do fairly complex things like transport, and actually normalizing it and distributing it in better ways, and so on and so forth. The pure software implication we've talked about as well, so I'm going to skip that, blah, blah, blah. Anyway, that's the end of what I wanted to talk about. I don't know if we have time for a few questions, but maybe we do.
So you talked about congestion control and back pressure between if the host is not taking versus internet, right? But I would assume you would have scenarios where there is many to one and one to many kind of traffic, right?
Yeah. So notice, so we have two answers for that. In the many to one case, let's say there was incast in the fabric, then we will deal with that back pressure in the exact same way. So that virtual queue will respond to ECN marks and do all the same things. So it'll all work out great. But the real trick for us is we actually should be incast free at all times, because notice what I said about the data path being parallel. So if you are talking to n GPUs with coherent memory, and those n GPUs have exactly n network ports, we can parallelize the full bandwidth. We will never see a many to one in that scenario. So as long as you're not targeting a GPU that doesn't exist, we should not have incast in our system.
So can you also talk about, you mentioned that there is advantages to combining the car and the NIC, right? Can you also talk about the power consumption wise? What's your car plus everything?
Yeah. So it's an interesting question. So in terms of just the SerDes, right? So there's two advantages. There's the power and there's latency. There is gone. There is no SerDes between the NIC and the switch. In addition, if you just think of the buffering, it's the same thing from a power and latency perspective. Right? The NIC always does a buffer, serialized into buffer, deserialized to wire, then buffer into the switch, and so on and so forth. We've combined those two stages as well. So the net effect of both the latency and power implication of combining these two are pretty significant, actually, in terms of overall systems. The downside, just to be complete and fair, the downside is that the way we have it currently constructed, we've optimized for maximum flexibility rather than absolute high-end power. And that's something that we are working on in our subsequent systems.
Did anybody say about single point of failure?
I can repeat the question. What about single point of failure? So notice my system diagrams always have two, and it looks more similar to standard switch fabrics where there is a AB fabric, and that's the way we are addressing single point of failure type issues. Our simulation, MDBF and other simulations are currently telling us 2 is a good enough number, but at the end of the day, it really is a function of, there is so many single point of failure components in our current ML system that this is actually not a significant change in any way, shape, or form. Anybody else? If not, okay, one more.
Thanks, Shrijeet. It was an excellent talk and really insightful.
Thank you. It's on.
Yeah, so my question is, considering this chip for inferencing, and since inferencing, it's not that you will always have the load coming in. How is there a mechanism for sharing this, like multi-tenancy this particular?
So we didn't talk a lot about how the system presents itself. So like I said, it's got 160 lanes of PCI and 32 lanes of 100 gig Ethernet. The way it presents itself, what is a port on the network side and what is a PCI port on the host side, is completely software managed. And you can have multi-tenant redundant implementations or redundant expressions where you can say, okay, this thing is for that sub-port of that physical port and then manage it that way. So yeah, multi-tenancy is something it can do. But that's actually, so what we are seeing is that's really not the use case that people are looking for. They're not trying to say, they put that inefficient, and it's also got two problems. It localizes, which means the GPU in the next host may be free, but you can't use it because your context is sitting there. And the second is this host, which has memory of its own, or memory transactions of its own, may see spikes in performance. So the way we are doing it is we pull the memory out, put it in the fabric, and now everybody can get to the context. So you can use the GPU that is sitting idle over there, and you don't have to worry about the host getting in.
I have one more question, but I don't know whether we so the other question that I had is in the architecture that you showed for Cerdis, the small gather architecture, there is a control plane component and a data plane component. And I'm pretty sure the control plane component will be slower as compared to the Oracle, right?
Yeah.
So, like, are there any inefficiencies because of that?
I mean, you have to have a control plane that is good enough, right? So, and fast enough. So the way we solve that problem is by carefully qualifying what we put in the control plane processor and making sure that it has the right IPC count, different IPC interprocessor or CPU efficiency IPC count such that we can sustain the control plane efficiency that we need. But the good news is, once you have such a number, I'm looking at other people like
I have to stop there. I can stop. So one last question is, I have this question that is there a possibility? You say that the buffer itself is enough to indicate a signal.
So the VOQ is basically saying, so the one place VOQs can be wrong is you could be saying slow down when there was only one more byte to send. Right? So, and so in the skid, you would have been able to absorb all of the left, whatever traffic was left. Let's say you were sending 1,000 bytes or 1,001 bytes. On the 1,000th byte, the VOQ said, oh, this is bad, slow down. You had only one byte to send, and the VOQ had headroom to be able to absorb that. You slowed everything down unnecessarily. And that is a tunable in our system. But that's a standard VOQ problem. In general, under steady flow, the VOQ will give you very, very good fidelity. We have configurable headroom, so it will try to figure out whether in the burst capacity that it thinks it's going to get, whether it should be able to absorb it or it should raise a higher level flag and say, go. Because we can signal, the signal that we send can say slow down or stop, and various degrees of slowdown. So as long as the signal is accurate, it should do the right thing.
Oh, thanks.
Okay, no worries. Thank you.
So I request Mr. Abid Kamaluddin to give goodies to the speaker.